All right, yeah, welcome back again. Here we want to look at parametric tests under two-way ANOVA. The last class, we looked at one-way ANOVA, which deal with one numerical variable and one categorical variable, which has more than two groups. But this time, we want to look at two-way ANOVA, which deals with one numerical variable and two categorical variables. So take note of that, two categorical variables. So let's just load this down. Right. So now here we understand this is an extension actually of a one-way ANOVA. Two-way analysis of variance which is ANOVA is an extension of one-way ANOVA that examines the influence of two different categorical independent variables on one continuous dependent variable. Take note of that. The categorical variables are independent variables, while the continuous variable is dependent variable, or otherwise called quantitative variable. All right, so if you more so, it is used to estimate how the mean of a quantitative or continuous variable changes according to the level of two categorical variables. So what is happening to that particular continuous variable? What is happening to it? Or rather, the effect of the two categorical variable on that continuous variable. The effect of these categorical variables on this particular continuous variable. That is what we are talking about. So we are going to use a tooth growth data set, okay, which comes along with our data set. Then no need to load, okay. Library, just call it directly. All right, it's automatically installed, and the library is automatically loaded by default. So some we load library by ourselves, some library is loaded by default, but this one is loaded by default. So you need to load library. Just call the data set. It's called tooth growth. All right, just call it. All right, so let's call it here. Let's assign this data set to let's call it peak data. Okay, let's give it a name. You can call it any name you want. So because it has to do with peak. All right, so let's before we glimpse, let us find out what it's all about. Okay, just say tooth growth here. So let's find out. Let's know more about this. The effect of vitamin C on tooth growth in guinea pigs. Right, so this guinea pigs, okay. The response is the length of odontome blast cell responsible for tooth growth in 60 guinea pigs. Each animal received one of the three dose levels of vitamin, which is of vitamin C, 0.5, 1, and 2 mg per day. So that is the do. We have three levels, 0.5, we have 1, we have 2, that 3 level of vitamin C. And we have so by one of two delivery methods, that is supplements now, orange juice or ascorbic acid. So a form of vitamin C and coded as Physi. So this is called that is called the supplement now. So we have the table name is called tooth growth, and a data frame is with 60 observations and 3 variables. The first variable is length, numeric. That's the tooth length. All right, this is the length of the tooth here, at the cell responsible for tooth growth. All right, we now have a supplement. This factor variable supplement, which is Physi, can be either Physi or OJ. What is Physi? Vitamin C, all right, or ascorbic acid. All right, so these are the two, either ascorbic acid or vitamin C. So we have dose, numeric dose, which is also supplement, which is also factor variable. Those can be 0.5, can be 1, can be 2 milligram per day. So these two are categorical variable now. These two, while this one is numeric variable. Okay, so that is how we data set is. So now let us describe it here. Let's glimpse it here and see what you are talking about. So look at it here. We have 60 columns. We have 60 rows, 3 columns. We have length here. Okay, it's the length of the tooth here, numeric. So you can see here We have a supplement here, C, okay, all right, vitamin C, or can be OJ, and we have dose here. Dose can be 0.5, it can be 1, can be 2, okay, per day, all right. So this is structure. Under each supplement we have dose. That's what it means. Under a supplement we have a dose, okay. So the supplement is used to administer the doses, all right. That is what it means. We are using the supplement to administer the doses. So either orange juice, okay, or ascorbic acid. So this orange juice, all right. Okay, so let's try to plot. Let us show a table of contingency and see how they are arranged. So if you are on this now, we have OJ, okay, we have FISI. These are the two category we have under supplements. Then under the doses we have, under the dose we have these three, right? 0.5, 1, and 2. So each of them is have 10, 10, 10. This is called balanced. This is balanced data set. Okay, this is balanced. All right. So we are going to attach our big data in case we want to use it directly instead of using $ to invoke our. So let's just understand the structure. So this is how the data set look like. So you can have your data set whichever way you have. Maybe you have a data set of weight or height of the children. Okay, the children now of people, for example, of children. Maybe you have we have gender, and you have age group. All right, gender, age group. I'm just giving you another example of where you can how you can get this data set. Okay, you have their weight or their height. So you have gender, you have age group. Under the gender, you can have different age group. Maybe male. A male can be a child, can be an adult, can be an elder. Okay, all right. A female can be a child, can be an adult, can be elder. Or you can also swap it. You can have a age group. You can have gender. Under each age group, maybe you have a elder. Elder can be either male or female. All right. An adult can be male or female. A child can be male or female. All right. So that is how. So you can now check. You can now find out under each weight, or under each the weight become the continuous variable, okay, or the response. So why the gender and the age group, or age group and gender becomes the categorical variable that you are going to use as your. So this is how it works, okay. And I think I have something like data test before. I think I have this from one of my data set I've worked with so far in this particular lecture. I have one of them, so you can check. You see how it was curated. Then you can use it as one of the additional alternative way instead of using this only. All right. The 2A ANOVA, like all other tests, assume that the observation within each cell are normally distributed and have equal variances. To check assumption first, we ask question: does the numerical data follow a normal distribution? All right. So let's use Shapiro test. Now we have attached our data, so we can use the line directly without using a $ to invoke it. So let's run this line. Shapiro test, we have 0.1, which passed the test. So we have the null hypothesis of the normal distribution is not rejected for our p equal to 0.1. Then so we can continue with the ANOVA test that assume normality. So let's just check equivariance and see that using our car library. So we use Levin test of equivariance. So Levin test, we pass in our length for the first supplement as our categorical data. Also use the same one for the dose. Okay, so let's pass in this. This part the test. Let's also for the second one also. That's part the test. All right. So, but that one is not factored yet, because if you check here, Levin test require that the two are factored, but this one is not factored. Look at it. This one is factored, but this one is not. So what do? You factor it here. Just say factor. So take note of this method I've been showing, so that you will not be having this warning. Okay. All right. So let's rerun now again. So the warning will disappear. All right. Normal warning. Okay. So So because it's required that the data set, the particular column is factored, because Levin tests deal with the categorical variable actually. So take note of that. So in this case, the null hypothesis of equal variance is not rejected for both groups. Okay, for both supplement and the dose. All right, we have a p-value of 0.2 and 0.5, which is more than 0.5, 0.05. So we can continue with another test that assume equal variance. Now, all right, so let's say we want to develop a research question. We want to know if tooth length depends on supplement and dose. Okay, if the tooth length depends on supplement and dose, so don't forget our definition when we first started. Okay, I mentioned some things here. Okay, it's used to estimate the mean of quantitative of or continuous variable changes according to the level of the two categorical variables. So we want to see the effect, okay, of the categorical variable on this particular continuous variable. All right, don't forget that. So we also say that it examines the influence of the two categorical variable, okay, which is dependent variable on the continuous variable. So how the categorical variable influence that continuous variable, which is a quantitative variable. Let's just be practical. Where are they now? Let's look at them one by one. Okay, okay, this ones. Okay. Let me just show you how the influence of supplement and this is on length of the tooth, length of the peak tooth. Okay, so that is what you want to look at. So let's go and continue. So we have run the test now. The test pass. So we want to know. So what we want to know if the tooth length depends on the or the effect of the supplement and dose on the tooth length. So let's create a box plot first and then check the means the division of each of them by group. So we can use this library also. So just another introduction of a new library. So you can use a GG pop R. So you can just call GG box plot. It's another powerful library for plotting different kind of plots like GG plots. So we can call our peak data, our S auto dose, Y equals to length, okay, we feed by supplements. So use the same structure for so let's run this. Okay, zoom, okay. We have a dose here, we have 0.5, we have 1, we have 2. Okay, so it's our dose. Also, we have 3 categories, okay, and we have length. Okay, so you can see here for supplement is supplement, and this is a supplement is 2. We have orange juice and vitamin C. Okay, you can see them. So this orange juice, vitamin C. I wish I would have wished that this color is orange juice, vitamin C. All right, never mind. So we have the two of them here. Don't mind the outlier, just one outlier here, one outlier here, so it doesn't matter. So it doesn't. It's not too extreme. Okay, it's okay. You can manage. All right. So this is the structure. Well, you can see that the mean is not the same. All right, the mean is. But even this one, it look as if the mean is very close for this one. The dose 2 milligram. You can see look as if it's very close to the supplement. All right, the supplement. Supplement. Orange juice and vitamin C. They look very close. So, but not exactly. All right. So let's plot and see the group by using the same method. Pick data with passing group by. We have two now. We have two category data now, not one. So now say supplement and the dose. We pipe painting. We summarize. We count. We find the mean, comma, like an SD of the length. All right. So when we run this now, should be able to have a table. Okay. Now, so look at the table now, giving us right. So we have supplements. We have dose. So you can see here. So you can see the mean of each of them. So that is how we structure it. So when you look at under 2, you can see that this particular one is 2 points. Mean is 2.6, 6.1. You can 26.1. You can see this is what I'm saying here. Can you see? Remember, I was pointing out this. So they are very close. They have equal mean. This one have equal mean. All right. So that's what it means. So in that orange juice and vitamin C, and this particular point you have equal. So let's just continue. So those things you must note those things so that we're able to have a proper analysis discussion. All right. So let's compute the two ways and analysis of failures now. What do? We use the same method, just part your AOV. Now, in this case, now we use our len as usual, but this time around we have two category data now, which is our we supply it here. We use plus together. Our data remains peak data. So we run this line of code. Right? So our result will pass it in here to summarize. See the summary. You can see here they are both significant, both supplement and dose significant. Right? So that is very clear. That is very clear. So you can report as the p-value of both are less than the significance level, 0.05. We can conclude that both supplement and dose are statistically significant. Dose is the most significant factor variable. You can see here, dose is highly significant. Having 1, 2, 3. Okay. These results will lead us to believe that changing delivery method supplement or the dose of vitamin C will impact significantly the mean tooth length. All right. The mean tooth length will be impacted by the changing delivery of the supplements. So it means both supplements highly affected the tooth length, especially the dose. Okay, affected. So that's the impact. There's a high impact of dose on the tooth length more than the supplements. That's what it means. Okay, so try to understand little by little those languages as I'm using them, so that you'll be able to familiar with it when you're interpreting. You have to interpret accurately based on the question at hand and the analysis and the problem. It can be seen that the two main effects, supplement and dose, are statistically significant as well as their interaction. So what do I mean by interaction? It means that I've removed interaction now. So can we do interaction? Let me see. Okay, just let us multiply. Instead of using asterisk, let's multiply so that you can see the interaction. So if you run this line of code now, it will give us each of these 1, 2, then give us interaction between supplement and dose to see if they are interacted well. So let's run this line again. Right. So we have this significant supplement. Dose is more highly significant. Okay. Don't forget very highly significant. Now, supplement and dose now interaction. So is it significant? Yes. 0.02 is less than 0.005, so it's significant. So there's interaction between supplement and dose as part of the effect of the length. That's what I was starting to discuss here. Okay, here. So it can be seen that the two main effects, supplement and dose, are particularly significant as well as their interactions are significant. So they interacted well. Then the p-value for the interaction between supplement and dose is 0.02, which you will see here. All right. Which is significant, which indicates that the relationship between dose and tooth length depends on the supplement method. You see that it indicates that the relationships between dose and tooth length depends on the supplement method that is applied. So that is that for that. So you can understand that, but in this case now, we can still maybe we want to do but this is a balanced data set now. Balanced design. So sometimes you can have unbalanced as equal number of subject groups. Sometimes the group is unbalanced. If you check the groups now, we have 10, 10. It's a balanced group. Look at it. Normally the group should be balanced under normal condition, but sometimes it's not always like that. Sometimes it's not balanced. So what do? You have to use other method. All right. So that is type 3. So an unbalanced design has unequal numbers of subjects in each group. So in the case that maybe you have now maybe 5 here, 10 here, and so on. So that means it's unbalanced. It is different from this application. So you have to use other method. Okay, that's when you now use let's say we use my ANOVA. We our same thing here. We multiply it data. But in this case, when we are done with this, what we do now, we now say ANOVA equals to ANOVA type 3. Okay, so let's run it and see what I'm talking about. Let's assume that they are not they're not balanced. Let's assume that they are unbalanced groups. Okay, so that you can see what I'm saying. So when you run this line of code, okay, we already assign our same thing we have run before. Don't forget this same thing. Nothing changes here. Okay, the same thing we have done before with the interaction. Okay, so we assign to this variable. Then we now call this function called ANOVA. Okay, this function. Okay, we call it without passing our ANOVA that we do before. We pass it in. We now say type is 3. We run this line of code. Right. So look at it here. So giving us this type test. All right, giving us our responses. Supplement significant, though significant, of course. Then interaction is also significant here. So this is what it's telling us now, because this is what when it's not balanced, we are assuming that it's not balanced. So just take note in case you find some of your groups that are not balanced. You have to first check for using contingent table to check first, as I did like I did just now. How do I do so? Look at it. I just run this contingent table now. This one, this line. Just run this, okay, and see if they are balanced or not. If you look at it, just run it. You know if they are balanced or not. If they are not balanced, then you have to use unbalanced method. Else, your result will be very wrong. Okay, so that is that for now about two ways ANOVA. I think that should be very simple and clear, and we should be able to handle that very easily. I think I'm going to stop here. So I will see us in the next class as we continue the lecture. Thank you so much. If you have not yet subscribed, you can go ahead and do that so that you can see more of the videos as we continue in different sections.